Good day, students. Welcome to part 2 of the last lecture on composite material. So you may recall in part 1 of this lecture, I have introduced the concepts of composite materials to you and some terminologies that you can use in describing what a composite material is. We have also looked at some examples of composite materials and classifications of composite materials. So we have looked at classification based on the origin, based on the matrix phase, and based on the reinforcement phase, that is the sparse phase. We have also looked at some of the factors that will determine the properties of a composite materials. So to simply an overview of what we did in part 1 of this lecture is that we understood the composite materials, the definition of composite materials, the terminologies involved, which is matrix and the dispersed phase. We understood the classification of composite based on origin, that is natural and synthetic composite, classification based on the matrix phase, metal matrix composite, polymer matrix composite, and ceramic matrix composite. We looked at composite classification based on the dispersed phase, which is the reinforcement. So I took you through a particle reinforced composite, fiber reinforced composite, and a structural composite, and then some of the factors that determine the property of a composite material. I explained to you that these factors include the property of the matrix material, the property of the reinforcement material, the ratio of the phases involved, that is the ratio of both the matrix and the reinforcing materials, the adhesion between the phases, and the nature of the design also will determine what the property of the composite material will be. So in the tail end of part 1, I took you through what a particle reinforced composite is, and how to mathematically estimate what the property of a particle reinforced composite will be. So with the use of the rule of mixture equation. So for both the upper limit and the lower limit estimation of what the composite material will be. So I also mentioned to you some example of composite materials like spheroidite steel, tungsten carbide, cobalt, reinforced rubber. So we have treated this in the part 1. So the part 2 now will focus on the other classification of composite materials. So here we are going to kickstart with the fiber reinforced composite. So for a fiber reinforced composite, so in this case you have a fiber as the reinforcement phase or the disperse phase, whichever one that is convenient for you, and then you have the matrix phase. So like I've explained in the part 1 of this lecture, for a fiber reinforced composite, you can have a continuous and aligned fiber, or you have a discontinuous and aligned fiber, or a discontinuous and randomly oriented fiber. So this is a continuous fiber that is aligned. This is a discontinuous fiber. Okay, let me get my pointer. This is a continuous fiber that is aligned. This is a discontinuous fiber that is aligned, and this is a discontinuous fiber that is randomly oriented. So also we need to understand how to estimate the property of a composite material if it is fiber reinforced. So we are going to look at that in this case. Now you will observe that the property of the material will be dependent on the direction of loading for a fiber reinforced composite. So you see that we didn't look at this in the case of particle reinforced composite. So for particle, we just estimated the upper and the lower limit. So here our upper and lower limit will correspond to the direction of loading. So you should expect that the property you will have, the resulting mechanical property you will measure if you load along this longitudinal direction, will be different from when you load along this transverse direction. So these two will now constitute what the upper and the lower limit will be in the estimation of the properties of a fiber reinforced composite. So for the fiber reinforced composite, what defines this composite is that you have the reinforcing phase as a fiber. So the fiber is simply a small diameter material that is stronger than the bulk in most material. So what it means here is that the fiber is stronger than the bulk material. So usually the fiber is made out of a bulk material generally. So but what has been observed from research is that the fiber is usually stronger than the bulk material. So especially if the material is a brittle one. So the question is, why is this the case? The answer is very simple. This is because the bulk material will exhibit more flaw than the smaller one. That means the defect in the big material will be much more than the smaller material. So what you have is that the smaller the material, the less flaw you have, so the better the mechanical property. That is why even today in modern day engineering design, you are going into as far as nano material. So it means the smaller the material is, the less flaws that you have in it, so the better the properties will be. So that's why you are looking at things like nanomaterial. So why nano? Because you have better properties with nanomaterial, and the reason is because of the less flaws that you have as you reduce the size of the material. So these fibers can be in different form. You can have them as whiskers. So for whiskers, you have very thin crystals that has large aspect ratio. Aspect ratio is in terms of the diameter and the length. So that's what you mean. So the degree of crystallinity and the flaws in it are very, very small. So it have an exceptionally high strength. So usually it is expensive when you talk about whiskers. Typical examples of whiskers are graphite whiskers, silicon carbon, silicon nitride, aluminum oxide, and so many other examples. So you can also have them. Usually when you have short fibers, you refer to them as whiskers, and then when you have continuous fibers, you just refer to them as fibers. So you can have polycrystalline or amorphous materials representing fibers. So they could be polymers, they could be ceramics, whatever. So you can have wires also in form of continuous fiber. So the wires will have really large diameter. So for example, typical wires that you have are the fine wires. So steel, for instance, is a typical example of fiber. So let me give you a typical example of where steel is used as a fiber. So in reinforced concrete, so you see that metal that is used in reinforcing concrete. So if you want to build, if you want to design a building, and then you need to make a concrete, the concrete is made up of the concrete is usually reinforced, because the concrete is going to give you a very brittle structure. So in order for you to and the brittle nature is attaining the brittle nature because of its high strength. So what it means is, even though it has high strength, because it is brittle, anytime there is a crack setting, the crack will propagate easily. So in order to toughen that concrete, you reinforce with a ductile face. Now that ductile face is usually the steel. That is why you see in a construction site you have a steel used to reinforce a concrete. So you see that steel there is playing the role of a fiber reinforcement in the concrete matrix. So this is a typical example of where you have steel as a fiber in reinforcement. Now the matrix face in a fiber reinforced composite can be metal, can be a polymer, can be ceramic. So typically metals or polymer are usually used, are often desired, and it's simple because you can play around with metals and polymer. You can make a liquid metal, you can make a liquid polymer, and then put in the reinforcing face in any way you want it, whether in terms of a whisker or in form of continuous fiber or whichever. But you see, it's difficult to achieve it with ceramic material, but nonetheless there are still fiber reinforced ceramic material, especially where you want to toughen the ceramics. So this is very important. So what does the matrix do in a fiber reinforced composite? What it does is, the fibers are dingsing, so the matrix holds the fibers together. It is able to transmit and distribute the load that you are imposing on the composite to the fiber, and then it protects the fiber from damages from either abrasions or chemical attack on the composite material. So usually in ceramic matrix composite, the fiber is there to improve fracture toughness, and I'll explain what this is. So fracture toughness is a unique property of materials that allows it to resist crack propagation. So you will now understand that in ceramic material, the ability to resist crack propagation is very, very low. The answer is simple. They are high strength, they are brittle. So what it means is once a crack sets in a ceramic material, the crack just propagates easily. So by that, it means the fracture toughness is very, very low. So one of the reasons for fiber reinforcement in ceramic material is to toughen it. By so doing, you want to improve on the fracture toughness. So you want to improve its ability to resist crack propagation. So once you do this fiber reinforcement in ceramic material, this is what you intend to achieve, so that the second phase you are inculcating into the ceramic material will now serve as hindrance for the propagation of the crack. So this is the effect of fiber reinforcement in a composite. So we talked about the effect of the interface as a unique factor in the determination of the resulting property of the composite material. So the fiber matrix interface is very, very important in achieving a good properties for the composite material that you have designed. So how do you achieve these fiber, the properties of the interface? So there are so many ways to improve or to affect the interface property. So the first is what you call molecular entanglement, that is interdiffusion between the matrix and the fiber. So here you have entanglement of molecule at the interface. So you have the molecules of the fiber being entangled with the molecules of the matrix. So here what you have is that the fibers that are you have fibers that are pre-coated with polymer. So what you do is that you do some surface adjustments to the fiber that allows it to be able to mingle well with the matrix, or you have some conformation or structural adjustment on the surface of the fiber of the polymer to allow this entanglement to occur. So let me give you a typical example. If you go to construction sites, you will see that the metal material that is used as a reinforcement for concrete is not smooth. The surface is more smooth. There is a design on the surface of the material. That design is intentional to allow for, it's a kind of structural conformation of the surface of the fiber that allows it to be able to entangle with the matrix face, so that you have a better grip between the two faces. Now another way of improving on the interface property is to have electrostatic attraction between the matrix and the fiber. So this will obviously be dependent on if there is possibility of any charge on the surface of the two faces. So if you have this kind of if you have a case where the surface are charged, then the attraction can affect on the interface property. So typical example is fiberglass polymer that has chargeable groups. So because of these charge properties, they can attract each other and have effect on the interface property. There's possibility of covalent bonding. So usually the strongest fiber matrix reaction can be obtained with this. So if there is a way where, remember that in the formation of composite material A and material B are not reacting with each other, but you can have a situation whereby at the surface there can be some kind of bond formation at the surface that will help improve on the interaction between the two. So this can have a large effect on the interface property of the composite material. Then there's possibility of mechanical adhesion, where you have an interlocking of the two faces. So if you have a situation whereby the two materials are rough and such that they can lock up, they can interlock themselves. This typical example is you allow them to set with this kind of look at this design. For instance, instead of you to just have a smooth surface, you have a rough design on the interface. So when they say, what is happening is one is locked in the other, so this will means that it is difficult to break these bonds between them. So this is a typical way of improving on the interface properties. This is very important because in fiber matrix, in fiber reinforced composites, while you focus on the matrix and the fiber property and the volume ratio of the two, it is also important to work on the interface property, because this will have very severe impact on what the property of the fiber reinforced composite will be. Okay, now how do we distinguish between what is a short fiber and what is a continuous fiber in a fiber reinforced composite? So the properties depend on the length and orientation of the fiber. So whatever fiber reinforced composite you are building, that property will be dependent on the length and the orientation of the fiber. So what it means is that the property you will get from a continuous fiber is different from what you will obtain from a short fiber. So what you will get from an aligned fiber will be different from what you get with a randomly oriented fiber. So this is very important. So as a result, we need to understand how do you define a continuous fiber and how do you define a short fiber. So basically, you define a short fiber or a long fiber by understanding what the critical length of the fiber is. So once you estimate the critical length of the fiber, that critical length will now allow us to obtain what constitutes a short fiber and what will constitute a continuous fiber. So the critical length of a fiber is given by sigma f multiplied by the diameter of the fiber divided by 2 multiplied by the interfacial shear strength between the matrix and the fiber. So if you want to design a composite material, you must understand what the interfacial shear strength will be. Usually this interfacial shear strength can be determined by doing a pull-out test. So if you have the fiber within the matrix and you do an experiment to pull out the fiber from the matrix, so the force that you will use to pull out the fiber from the matrix and the dimension of the fiber will allow you to calculate the interfacial shear strength of the fiber. So if you know the fiber strength, if you know the strength of the fiber, you know the diameter of the fiber, and you know the interfacial shear strength of the fiber. So this interfacial shear strength can be either the bond strength between the fiber and the matrix, or the yield strength of the matrix, any of these two, but the smaller of them. So if you calculate these two, one will be small. Whichever that is smaller is what you will take as this tau c. So now once you put all of this in this equation, you will get the critical length. Now once you obtain the critical length, the question now is, if you want to now design a continuous fiber reinforced composite, you have to now make sure that the length of the fiber should be far greater than LC. So it means that once you now use a length that is far greater than LC, then your composite will now be regarded as a continuous fiber reinforced composite. But if you want to design a short fiber, so you design a short fiber by making use of a length that is less than 15 LC. So once you measure 15 LC, any length less than 15 LC will be defined as a discontinuous fiber. Any length that is far greater than LC, so it means it must be greater than this 15 LC. So any length that is far greater than LC will be termed a continuous fiber reinforced composite. So if you have a fiber reinforced composite, this is how you know whether it's a short fiber or is it. Actually, you have to decide in your design whether you want to design a continuous fiber reinforced composite or you want to design a short fiber reinforced composite. So if you choose to design a short fiber reinforced composite, you now have your fiber length less than 15 of the LC, and if you want to design a continuous fiber reinforced composite, you make sure that your fiber lengths are far greater than LC. So for a fiber reinforced composite, possible failure modes is the breaking of the fiber within the matrix, or the breaking of the failure of the matrix, or once the fiber pulled out of the matrix, you have a failure. So what is the impact of this fiber length? So the fiber length has a great implication on the property of the composite material. So what you should understand is that if you have short fibers and you have long fibers, they have direct implication on what the property of the composite will be. So for short fiber composite, the efficiency of the fiber will be very low, and for long fibers, the efficiency will be better. So what it means is that if you take the length of a composite material, if you take the fiber length to be equal to the critical length, what it means is that once you load the composite material, once you have applied a stress that is equivalent to the strength of the fiber will fail, and then the composite will be tending to failure immediately. Once the length of the composite material is equal to the critical length, this is what you have. But if the length of the material, of the fiber, if the length of the fiber is greater than the critical length, what it means is that if you load the composite up to the strength of the fiber does not fail immediately. It means that the fiber will still be functioning within the matrix without failing before it will now eventually fail. So it means that you still have some time to continue to use the fiber will still continue to take in loads without failing before it will eventually fail. But if you now decide to make the fiber length to be less than the critical length, then what you will have is that you will not even have optimum usage for the fiber. So what it means that the stress that will fail the fiber will be less than the strength of the fiber itself. So it will fail within the matrix without actually taking up strength that is up to its own strength. So that is why you will see that even in the formation of, even in the use of a short fiber, you want to make sure that the length of the fiber is less than 15 LC, so that you still have at least something greater than LC. I hope you get this. So you don't want a critically short fiber so that you don't have a poor fiber efficiency. You want something like this with a better fiber efficiency. So if you have aligned fibers, is either it is continuous or it is discontinuous. We have explained it. So what is the implication of having this fiber? The implication of having this fiber is that you want to have an aggregate property from the matrix and the fiber. So what happens is, if this stress strain curve is defined that this is the curve for the fiber, this is the curve for the matrix. So if you now produce a composite out of these two, you will have a composite with this property in between. So here you see that the fiber is high strength but less ductile. Here you will see that the matrix is ductile but less strength. So if you now produce a composite out of these two, so you have a composite material that has a better strength when you compare with the matrix, and better ductility when you compare with the fiber. So you have an intermediate property here in the middle. So this is the direct implication of fiber reinforcement in the matrix. So if you want to carry out an analysis of the properties of this fiber reinforced composite, you will see that the orientation is very, very important. That is the direction of loading. So if you have a fiber reinforced composite such that the fibers are aligned for this particular diagram that you are looking at, what it means is that you are going to have maximum stress when you load along the direction of the fiber. You are going to have minimum stress when you load perpendicular to the fiber, and then you have a range in between the maximum and minimum based on the orientation of the fiber. So this is the next thing we are going to look at. So for us to estimate the property of the fiber, we are going to start from the easiest one, understanding the properties based on a continuous fiber orientation. So for a continuous and aligned fiber, so this is what you have. You have the fiber is this colored part, and then the white part is the matrix. So if you consider a composite with fiber that is having a square rod geometry, and then you have the stress applied such that it is in line with the fiber orientation. So here, remember, we are talking about a continuous fiber. So what we mean here is that the length of the fiber is greater than LC. So what we need to understand is that there are two conditions that we are going to consider in estimating what the property of the composite material will be in this case. So the first condition is called the isostrain condition. The second condition is called the isostress condition. So we'll look at the isostress as we go along. So for the isostrain condition, so as the name implies, isostrain, meaning that equal strain. So you will obtain an isostrain condition when the load application is in the same direction as the orientation of the fiber. You will obtain isostrain condition. So what this isostrain means is that the strain that you incur in the composite is the same as the strain in the fiber. It is the same as the strain in the matrix. So it means you have equal strain in the fiber and the matrix, and that is also going to be the strain in the composite material. So that's why you have EC is equal to EF is equal to EM. E in this case now is the strain. So remember that strain is change in length over original length. So it means that the E of the composite is change in length of composite of the divided by the original length is equal to change in the length of the fiber divided by the original length, and is equal to the change in length of the matrix over the original length. Okay. So if we consider the load application on this longitudinal loading, where the loading is such that it is along the fiber, it is in the same direction as the fiber, it's on the same orientation as the fiber, the implication is that the total load on this composite material will be equal to the load on the matrix plus the load on the fiber. So the total force on this composite material, remember we're still considering we're still talking isostrain condition here. We're still talking isostrain condition here. So what it means is the total load under this condition will be equal to the load on the composite will be equal to the load on the matrix plus the load on the fiber. So remember from our mechanical property that stress is force over area. So therefore force is equal to strength multiplied by A. So stress multiplied by A is equal to force. So we replace these forces by stress multiplied by A. So it means that the F of composite becomes sigma C multiplied by AC. The force on the matrix becomes sigma M multiplied by AM, and the stress on the fiber becomes sigma F plus AF. So we are using this to generate this. So recall that there's a relationship between stress and strain, and the relationship is the proportionality relation between, which is Hooke's law. Stress is equal to modulus multiplied by strain. So if you replace this stress here by EE with modulus multiplied by strain in this equation, you will obtain this equation. So you have modulus of C multiplied by strain of C multiplied by the area of C, that is this, will be equal to modulus of M strain of M multiplied by area of M, which is this. And then you have here modulus of F, strain of M multiplied by A of F will be represented, will represent this particular part. So if you see this now, you can rearrange. In order to get the modulus of the composite, you divide all through by strain of C and area of C. So if you do that, you will get this. So the modulus of C now becomes this plus this. Now, if you remember, we said this is isostrain condition. So it means the strain in composite is the same as the strain in the fiber, and is the same as the strain in the matrix. So it means that strain of M and strain of C is the same. So this will cancel. The strain of F and the strain of composite are the same. So this will cancel. So we are now left with EC is equal to EM AM over AC. And then our EF will be here, and you are left here with AF over AC, which is this. So now you see this AM over AC is an area fraction of the composite, of the volume. This is area fraction of the area of the composite material, which can also translate to the volume fraction. So if you do that very well, what it means is that I don't want to bore you with all of this. All of this expression is trying to express the cubic structure here in terms of area, the area fraction. Try to convert it to volume fraction. So because of time, what you should understand is that the AM over AC is a fraction of, is the area fraction of the matrix on the total area of the composite material. So by implication, AF over AC will also be the fraction occupied by the area of the fiber occupied in the area of the composite material. So this translates directly to volume fraction. So your AF over AC becomes the volume fraction of the fiber, while your AM over AC translates to the volume fraction of the matrix. So if you do that, your elastic modulus in the longitudinal direction under isostrain condition will now be equal to Vm EM plus Vf EF. So you see, this now translates to the rule of mixture condition that we have with the upper bound for particle reinforced composite. So you see, we're having the same thing, except that in this case is fiber. So for longitudinal loading where there is isostrain condition, this is what we will use to predict the modulus of the fiber reinforced composites. So now when you have this case, remember we say that the total force on this composite material is the force on the fiber plus the force on the matrix. So remember, one of the function of the matrix is to transfer load to the fiber. So what it means is that if you load the composite material, the total load that you have put on the composite, some will be retained by the matrix, others will be transferred by the to the fiber. So it is important for us to understand how much fraction of the load is taken by the fiber and the matrix. So to estimate that, you will use this equation. So the ratio of the load taken by the fiber with respect to the ones taken by the matrix can be obtained by EF VF over EM VM. So this will give you the ratio of the force taken by the fiber to that taken by the matrix under isostrain conditions. So the other loading condition is called the transverse loading, which will give you the isostress condition, transverse loading. So for transverse loading, rather than having the load application along the line of the fiber, you have it transverse, perpendicular to the fiber direction, the way you have it in this diagram. So in this case, you have isostress. So isostress here means equal stress. So what it means, if you load with this configuration, you will have the same stress in the composite, the fiber, and the matrix, all equal. So the stress in the composite, the stress in the fiber, and the stress in the matrix will all be equal. So in this case, you have equal stress in this particular loading configuration. So in this case, what it means is, so here, the stress is the same all through, so therefore the force is the same all through. So what will be changing here is the deformation. So the total deformation in this composite material will be equal to the deformation in the fiber plus the deformation in the matrix. So it means the fiber would deform differently and the matrix will deform differently. So the total deformation will now be the deformation in the fiber plus the deformation in the matrix. That is what you have with this equation. So now this will mean that the strain is different. So the strain in the composite will be different from the strain in the fiber and will be different from the strain in the matrix. So the total strain now in the composite material will be equal to the strain in the fiber plus the strain in the composite material. So this is what you have. So your EC will be equal to change in LC divided by the original length of LC. So, and this will be equal to change in LF divided by the original length of F, change in LM divided by the original length of M. So this is what you have. So here too, what you will have is that your LM. So what you have is you need to also express. You need to do some expression of volume fraction here. So this is what we get originally. So this is EC as a function of EF and EM. So what you do here is that if you divide all through by volume, if you divide all through by volume. So what you will notice here is that this particular LC, if you divide all through by LC, what you will see is that the LF that you get here, will be a fraction of the LC, and then your LM is going to be a fraction of LC, just the way we are having it here. So you see, this LF over LC will now become like a fraction that can be expressed as a volume fraction. So the same thing you have with the matrix. So at the end of the day, the strain here will now be equal to Vm over Em plus Vf over Ef. So the strain now is different. The strain is different. So the strain now is a function of V, which is the volume fraction of the matrix and the volume fraction of the fiber, along with the strain of the matrix and the strain of the fiber. So what you now have here is that in order for us to now express this in terms of stress or modulus, we now go back to our stress-strain relation, where strain is stress over modulus. So if you change this strain of the composite, it now becomes sigma c over the modulus of c. The strain of the matrix here will now becomes the stress of the matrix divided by modulus of the matrix, and then the strain of the fiber here becomes the stress of the fiber divided by the strain of the fiber. So if you do this now, remember that this is isostress condition. Pardon me. So this is isostress condition. So by isostress condition means that sigma c is equal to sigma m and is equal to sigma f. So all of this sigma will cancel out. So you are now left with 1 over EC will be equal to Vm over Em plus Vf over Ef. And then if you make EC the subject of the formula, you get this equation as the transverse modulus for isostress condition under transverse loading. I hope this is clear. So this is for isostress condition. So by isostress condition means that this sigma c, sigma m, and sigma f, they are the same, they are equal. So they will cancel out from this equation. So once they cancel out from this equation, what you are left with is 1 over EC is equal to Vm over Em plus Vf over Ef. So if you now make EC the subject of the formula, you will get EC this time around in the transverse section to be equal to Ef divided by Vm Ef plus Vf Em. So this will now give you the predicted modulus for the loading configuration under transverse conditions for isostress condition. So if you now try to compare this with what you have with the particle reinforced composite, you will see that the longitudinal loading and the transverse loading is equivalent to your upper and lower bound conditions for particle reinforced composite. So what this means is that if you want to predict the property of a composite material, you will use both the transverse loading condition and the longitudinal loading condition to predict what the property will be for a particular volume fraction under consideration. So the implication is whatever value you obtain from the two will be the range that is expected when you now practically design the material and you put it through an experimental condition to determine what the property will be. So the essence of this rule of mixture theory is that it now allows you to be able to predict the property of the material. So what it now means as a summary in general is that many properties will follow this upper and lower bound relation for continuous aligned composite. So our upper bound is now equivalent to the longitudinal loading condition, which is the isostrain condition. That is this. While our lower bound will now be equivalent to our transverse loading condition, which is the isostress condition. So what you will see is that, so this is a general definition. If you have a continuous fiber reinforced composite, please take note, I'm insisting, this is for continuous fiber reinforced composite. So what you have here is, you see this X now is the property of the composite material. So this X can be modulus, can be the strength, can be the thermal conductivity, can be electrical resistance, whatever property it is for the composite material. That is what this X stands for. So Vm is the volume fraction of the matrix, VF is the volume fraction of the fiber, and then XM is the property of the matrix, and XF is the property of the fiber. So this is what you have for the upper and the lower bound, in this case corresponding to the longitudinal loading condition and the transverse loading condition. So now what happens if it is not a continuous fiber? One, what happens if it is not continuous and it is not aligned? So this is where this is where you now begin to do advanced composite material. So what we have done now is the simplest form of a composite material. So what it means is this aligned composite can become discontinuous. So it becomes short fibers but aligned. Once that happens, these equations will change. Now, if the equation changes, if you now begin to consider the orientation of those short fibers, so if they are not aligned, it means that they are randomly oriented. So it means that some other parameters will also come in. So because this is an elementary class, we are not going to go deep into that. We are going to stop here. So but you should understand that once all of those other conditions come in that changes the architecture of the reinforcement, these equations will still be valid. All that will just be needed is some mathematical adjustments that are going to be based on experimental facts that will come into consideration. So this is like the foundation for understanding the mathematics involved with the prediction of properties of composite material. So I urge you to go to the textbook Callista. You will find some worked example in there that will allow you to practice some of the problems there. Then there are some exercise also that will help you to understand better this equation. So I hope this is enough to give you some basic understanding of what a composite material is. So as an end to this class, what are the things I want you to put in your mind is that we have understood a composite material, and we now know what matrix and reinforcements are. We know the classification of composite material based on the matrix or based on the reinforcement. So, and also based on the origin. So based on the origin, we understood that there are natural composites and there are synthetic composites. Based on the matrix, we have understood that you have MMC, metal matrix composite, we have CMC, ceramic matrix composite, and we have a PMC, polymer matrix composite. So for classification based on reinforcement, we know there are particle reinforced composites. We have understood the rule of mixture that allows you to predict the upper and the lower bound for the modulus of a particle reinforced composite. And then for fiber reinforced composite, we understood that there are continuous and aligned composite, there are discontinuous aligned composite, and then there are discontinuous random fiber reinforced composite. So we understood how the effect of the fiber dimension can have dimension can have on the property of the composite. So based on that fact, there is need to understand what constitute a continuous fiber and what constitute a short fiber. And the primary understanding there is the critical length of the fiber, and that will allow you to determine whether the fiber is continuous or discontinuous. So also we understood how to estimate the property of a fiber reinforced composite, taking into consideration the simplest condition for a fiber reinforced composite, which is an aligned and continuous fiber reinforced composite. So we looked at loading conditions under longitudinal and transverse loading, and we try to generate what the property will be under isostrain and isostress conditions. So we didn't do so much on structural composite, but at least I have introduced what a structural composite material is to you. So this is where I will stop for this particular lecture, and this is supposed to be an introductory course to engineering material. So hopefully in your higher classes you will do more, especially where you are going to be putting into application a composite material. So I hope that these online lectures have served you right. The intention is to have you have some concepts from me, and then of course it will aid in your understanding of the course, and when you read it will be easier for you. So as a last note to you, I want to encourage you to read the textbook and other materials that you have at your disposal, and you should feel free to talk to me on any of these topics that we have treated online. And hopefully we can say for now that we have been able to complete the classes as instructed by the school management. And I want to encourage that you should reach out to me. If you need further explanation or assistance in any part of the topics presented online, and even the ones that have been presented offline. So I encourage you to reach out to me. I think WhatsApp has been, so far I've received feedback from some of you through WhatsApp, and I think I've been able to respond accordingly. So I encourage you to please talk to me. So I encourage you to please talk to me via WhatsApp. You can send voice notes, you can chat with me. I'll be available to respond to any of your questions. Please, if you don't have the contacts to talk to me via WhatsApp, please, I don't want to give out my contacts on this forum, so please, you can talk to Investor, the class rep. He's going to give you my WhatsApp contact, so you can easily talk to me via that platform, and I'll be available to respond to any of your questions, and that will assist you in understanding this course as much as. So at this junction, I want to sign out of this class, and happy that I eventually got a platform to round up the class. So please revise everything that we have done. I wish you all the very best, and I hope that some of the things that you have learned in this class will assist you in your further studies, in your pursuit of a degree in engineering. So please continue to keep safe, and hopefully we will get back to our normal life, and we'll do things the way we are used to doing. But in the meantime, please, I encourage you to continue to keep safe. Let us obey all the guidelines and protocols as issued by the NCDC. I pray that we don't have a share in this pandemic that is ravaging the entire world. I wish you all the very best, and have a lovely day, and I wish you the very best. Bye bye.